Okay. So what were we discussing in the last lecture? We discussed about acceleration of a particle, within a rigid body in pure rotation using the cross product methods. We discussed kinematics. So we had seen that if this is, let's say, a rigid body and it is rotating about a fixed axis like this, okay, then for any particular particle, let's say P located over here, whose position vector is R. So for that particular particle at this instant of time, the radial unit vector becomes like this R cap, and the tangential unit vector becomes like this theta cap. Okay, and the axial unit vector for the omega and alpha becomes n cap. So n cap is equal to R cap cross theta cap. So in this case, you can see it is coming out of the plane. Whereas had it been like this, then theta cap would have been down like this and n cap would have been going into the plane. Okay. So on that basis, we can see that we can define the position of the particle, obviously we know, but we can define the velocity of that particle as a cross product as omega cross R. Or we can also express it as R omega theta cap, okay, like this. So we have speed is equal to R omega. Okay. Whereas we can define the acceleration of the particle as the sum of the centripetal component of acceleration plus the tangential component of acceleration. Okay. And the centripetal component of acceleration is then given by omega cross V or omega cross R, or in much more simple terms, it is minus R omega square R cap. Okay. Whereas the tangential acceleration is given by alpha cross R or R alpha theta cap. Okay. So all these cross product relations can be understood by just using the circularity of this. That R cap is equal to N or N cap is equal to R cross theta. So R cap can be written as theta cross N and theta cap can be written as N cross R cap and all that. Okay. Now, one of these things we've already seen the implication of when we are discussing about kinetic energy of a body which is rotating. So if we consider our particle as if it has mass dm, so we already saw that the kinetic energy of that particle is half dm v square. So when we integrated that, omega is common to all the particles, so it became what, half omega square into integration r square dm, and that's how we got the quantity of moment of inertia. Now from there we'll move on to dynamics now. So in dynamics, what we want to basically understand is that if this rigid body is in pure rotation about this fixed axis with some angular acceleration alpha, so obviously there is some external cause for that effect. No? Like when translation is happening with linear acceleration A, that means the net force acting on the particle is non-zero or on the body is non-zero. So like that, when a rigid body is rotating about a fixed axis with some alpha, so that is, it's in a non-uniform motion. No? If alpha had been 0, we would have said it's rotating uniformly. Just like if A is 0, we say it's translating uniformly. So it has a constant momentum. So like that, if omega is constant, later we'll say it has a constant angular momentum. But here we are assuming there is some alpha. So there must be something external which is pushing it to give it that alpha. Now, like right now, this door is at rest. Now I want to set it into motion. So I want to increase its omega from 0 to non-zero quantity. So I have to apply some force in a certain way. Now what I notice is that the force I apply, how much effect it has in terms of rotation, that depends on a lot of things. For example, it depends on the mass of the door, but also depends on how the mass is distributed. Now, like let's say let's imagine this was a very heavy block. Okay. Now instead of attaching it here, if I had attached it here, the door would have appeared to be much heavier now, because moment of inertia would have increased because the same heavier mass is now at a further distance away. So it not only depends on the mass of the door, but also on the distribution of mass, and that's where moment of inertia depends. Okay. Now another thing it depends on is where I'm applying the force. For example, the handle is right at the end of the door, so I'm applying the force and it's conveniently having a long momentum. So it's something like this. If to set this into motion, I were applying a force over here, I would see that to gain a certain alpha, a minimum value of F would do. But instead of applying that force there, if I was applying that force over here, where that line of action of the force is pretty close to the axis of rotation, then this force would not be so effective. So it's like if I put the handle of the door over here, then I'd require a lot more force to pull it open. So that means the effect that the force has in terms of rotation doesn't depend only on the magnitude of the force. It also depends on where I'm applying the force. And incidentally, also it depends on the angle at which I'm applying the force. For example, if I was applying the force like this, or in other words, I was applying the force like this, so I can apply however much force I like, but it's not creating any rotation because the line of action of the force is passing to the action. Okay, so this shows us that there is some kind of relationship between the force, the point at which I'm applying the force, and the direction in which I'm applying the force. These three things put together are telling me how much effect that force will have, not just the magnitude and direction of the force. Okay. So how to explore that? So that is where the dynamics comes in. That is where, our next thing today comes in, that rotational dynamics. So we'll understand that how the external forces that we are applying on the body affects the angular acceleration. What is the relationship between these two? Okay. So moving forward. Okay. So we've got our same rigid body. And let's say it's got a fixed axis over here. So this is now what I start doing is I start applying some external forces. Okay. And need not be just one or two forces, there can be n number of forces. So I'm applying F1 at a particular point here. I'm applying F2 at a particular point here. Okay. I'm applying F3 maybe like this. You can see that some of the forces are even competing. The way I've shown the diagram, you can see that F1 tends to create anti-clockwise rotation about this axis of rotation. But F2 on the other hand is also tending to create anti-clockwise. But F3 is tending to create clockwise. So they're kind of trying to cancel each other, the effects of these forces. So what effect this will have in terms of the rotation? How much alpha this will produce? So let's understand that. So to understand that, we come back to start to an individual particle within the rigid body. So instead of the entire rigid body, now if we see within the rigid body, we are considering one single particle of mass dm, okay, which is located at a position vector r, okay, with respect to our fixed axis of rotation. And this is rotating with omega and alpha at the given instant. So how we'll apply particle dynamics to that small particle? Net force is equal to mass into acceleration. Okay, so net force on that particle, let's say, is df, because it's a differential particle. Okay, so it's in circular motion like this, so I can assume the net force will be something like this. Because assuming that it will have some centripetal as well as some tangential acceleration. Okay, so that net force acting on that particle is equal to its mass into its acceleration. And further, we've seen its acceleration is what? It is the sum of centripetal acceleration plus tangential acceleration. Okay, which for simplicity, I'll just write like this. Instead of that cross product thing, I'll just write it as minus r omega square r cap plus r alpha theta cap. So this is what I'm getting, where this quantity df, this is what? This is the net force acting on the particle, let's say P, where P is this particle. Okay. Now notice what I wanted. I wanted a relation between forces and alpha, whereas this is giving me a relation which has omega also. So one interesting thing we can do here is that, and also you can see that alpha as a vector is outwards, whereas right now this is theta cap and r cap are lying in the plane. So I have to do some operation to this so that the direction of my vector comes outwards. It becomes axial in direction because alpha is an axial vector. No? What I want is I want to relate force with angular acceleration. Now, what is the direction of angular acceleration? It's outwards. It's axial. Whereas right now, this whole vector equation, the vectors are lying in the plane of the diagram. They're not lying along the axis. So what I have to do that to convert to getting something coming out of the plane, I have to take cross product with r on both sides. Okay, so if you see here, if I take r cross df, what is the direction of r is like this and df is like this. So what will be the direction of r cross df? Point your thumb along r and your fingers along df. So where your palm is pointing outwards. So I'll get a quantity which is coming out of the plane. Right hand side, I have to do the same operation. If I say vector A is equal to B, then r cross A is equal to r cross B. So when I do r cross on the other side, this term will disappear. because r cap cross r will give me 0. And what will r cross theta cap give me? It will give me coming out of the plane, and that is the direction of alpha. So I'll get alpha vector. So that will be one way to relate this force dF with the alpha vector by taking r cross on that side. So that is why then r cross dF is called what? It is called the torque due to this force dF acting on that particle. Now it's not the torque on the body because we are just considering one particle at a time. But if I take cross product with r on both sides, what I'm doing is on the left hand side, I'm doing a calculation which is called moment of force. I'll explain what moment of force is in more detail later. But for any force F, if you take the cross product with r vector, it gives you the moment of that force with respect to a particular point. And which is the point? The point from which we have considered the r vector. So whatever force is acting over here, I want to understand moment of force with respect to this point. So I'll define moment as what? R cross F. And doing the operation of r cross F, on the other side, you see, I'll get some quantity which is related to alpha. Okay, so that's the operation we'll do next. So you can just note down up to here if you want. Okay. So this is dynamics applied to the single particle. So this is particle dynamics. Okay, applied to the point P. So that is bringing us up to this point. But next step, what we'll do is to get rid of this omega square term and also to convert this vector equation into something where the direction of the vector is coming out of the plane. We'll take moment on both sides. That is, we'll take cross product with r on both sides.
Done, sir.
Okay, so next step, what we'll do here is we'll come back to this diagram later, but we will do the operation on this vector by taking cross product with r on both sides. Okay. So take cross product with r on both sides, where r is what? It is the position of the particle with respect to the axis of rotation. Okay. So when we do that, on the left hand side, I get r cross df. And on the right hand side, I'm going to get r cross dm into this whole thing minus omega square r cap plus r alpha theta cap. Okay. So when I do this cross product, you can see the first term will disappear and the second term will give me something which I'm very familiar with. It will give me dm into r square alpha n cap, because I know that r cap cross theta cap is equal to n cap. So I'm making use of this. Okay. So this vector is making a cross product with this unit vector, na, theta cap. So this vector r is actually r into r cap. So that's how I get the extra r. I have dm into r alpha into another r from here, but the direction of that becomes along r cap cross theta cap, so it becomes n cap. So I get a quantity which actually directly now depends on which directly now depends on alpha vector. It is dm r square into alpha vector. Okay, and that is my r cross df. Okay, so if this was a single particle system, this is its moment of inertia. Okay, and the df is the net force acting on that system. So r cross df would have been what we call a net torque, but here it's a multiple particle system, so we won't call it a net torque. Okay, now we will say that we'll make a new definition. The quantity r cross f, or r cross in this case df, we will define it as the torque due to the force df, okay, about the given axis. This is how we define the quantity torque. Okay. It is also called moment of force. So because it's a differential force df, so we have written it as a differential torque. Okay. In general, we can also say that for any force F, the torque is nothing but r cross F. So the moment of force is r cross product with that particular force. It is actually like the perpendicular component of force into the distance. We'll understand that later. So for example, if this force df which I've got over here, I divide it into a perpendicular component and a parallel component, or in this case anti-parallel component. So it will become like that perpendicular component of force into this distance r. So that is the magnitude of the torque, and the direction of the torque is always axial. So for example, if the force is acting in such a way that it's creating anti-clockwise torque, then my torque's direction will be coming out of the plane, the unit vector. Otherwise, it will be going into the plane if it's creating clockwise.
So the first term vanished because like the force and the position vector are perpendicular, right? That's why. No?
Sorry, come again. Which are perpendicular?
So the first term in that r cross.
Correct. N cap cross r cap. So, sorry, r cap cross r cap. That will be 0. That's how that omega square r cap term is disappearing. You understanding? Huh? You asking about that?
Yes, sir. Yes, sir.
Yeah. So see, when you take r vector cross product with minus omega square r cap, you know, so you're taking the cross product of two vectors which are anti-parallel to each other. The angle between them is 180. So their cross product will be 0. Okay. So basically, this term's cross product with this gives us 0, because they are anti-parallel to each other. This is minus r cap and this is r cap. Whereas this one's cross product with this term gives me this. Okay, so written this down. Right.
Yes.
So now once we come to this equation and we integrate this now. Okay, so we've got r cross df is dm r square into alpha on this side. Okay. Now remember what r was. R was the position of that particular particle on which the net force acting was df. Okay, and on the other side, dm and r square, simple, but alpha is the vector which is common to all the particles. Okay, so if I integrate this equation on both sides, what I will get now? I'm integrating this over all the particles. Okay, so I'm integrating it over the entire rigid body. And on the other side, when I integrate, alpha is a constant, so it will come outside. Now again, I'm integrating this over the entire rigid body. So this is what by definition it is moment of inertia. Okay, but what about this side? Let's come to this also. Okay, what about this side? This side is, now see, we are adding up R cross df for each and every particle. So that df on any particle includes which type of forces? Internal forces within the body and maybe external force from outside, depending on where the particle is located. Now, when I'm integrating over all the particles, what will happen to the torques because of internal forces? They'll cancel off. So I'll be left with only the torque because of external forces. So because we are integrating over the entire rigid body, so this will tell us that the R cross F due to internal forces will cancel. In action reaction pairs. So this integration of R cross df will now result in summation of R cross F for only the external forces. So what I'm counting over here will be only the external forces. I'll explain. Okay. Because see, particles are connected to each other. No? So where the interactive forces are acting, they're at the interface where they're connected. So the R's are same. Okay. So this is the net torque due to only the external forces. Okay. F1, F2. If there are n number of external forces acting, so only those external forces are going to contribute to this whole integration. So we'll make a visual picture of this also, and it will be easier to understand in that how exactly the torques are cancelling because of internal forces. Okay. Okay, so finally what I'll be left with over here.
So can you? So I didn't write actually. Can you just?
Yeah, you had it out, beta?
So I didn't write the previous part.
Yeah.
Done, sir.
Done. Okay. So now by definition, this quantity summation R cross F for all the n number of external forces, this will be called the net external torque. Okay. This is the net torque due to external forces. Okay. And therefore that equation becomes that net torque due to external forces is equal to moment of inertia into angular acceleration. This becomes the dynamical equation or the equivalent of Newton's second law for a rigid body which is rotating about a fixed axis. Okay. So this is dynamics of a rigid body in pure rotation. Where I is moment of inertia about that particular fixed axis. And in this equation, any individual term Ri cross Fi, it is like the torque due to the force Fi about the given axis. Okay. So in this, what is Ri? It is the position vector of the point of application where that force is acting. Again, with respect to the axis of rotation.
Done, sir.
One second, sir. One second.
Yes, any doubt? Okay, finish writing this down. All right, so let's understand this in a sort of visual way next. So suppose, we have something like this, like a rather thick rod or plank kind of thing. Okay, and we drilled a hole through one end and made a fixed axis over here. And initially it's on a smooth horizontal surface and it's at rest. To set it into rotation, we need to apply some torque. We need to apply torque through forces. So let's say there are a few forces acting, like there is a force. Yeah. This is. Come again. This is the top view, let's say. Okay, so this is the top view. We are looking into the horizontal surface on which that rod is lying and all that. Or you can even imagine it's just a rigid body with a fixed axis in gravity-free space. So if we let it be, it would just hang that way. No difference. Okay. So let's understand how that internal forces, external forces things works out first. Okay. So for example, or let's take it at a different point. So this force is now, let's say, acting over here. at this particular point, and this force is acting at this particular point. Okay. Now, if I consider any arbitrary particle, let's say I consider an arbitrary particle A over here like this, okay, and right next to it is another arbitrary particle B. Okay, so it's likely that A and B are interacting with each other with some kind of force. Okay, so let's say that the internal force that B is applying on A is in this sort of direction. So this is the force on A applied by B. So there's an equal and opposite reaction force that A is applying on B, and that will look like this. Okay, and both the forces are acting at the common interaction point, no, between them. So for both those forces, what is the position vector? It is this one. No? Is this common R vector. So when I'm doing that thing, when I'm doing that integration R cross VF term, okay, how will the contribution of these two come in? These will come in as R cross FAB plus R cross FBA. Okay. And now when I use this term that this and this are opposite of each other, they'll cancel each other. So this contribution will be this will give us 0. Okay. Whereas the other two, they are contributing something, because this is now the reaction to this particular force is not acting within the body, it's acting outside the body. So this is an external force. Okay. This one is also an external force. So the point of application of this is at position vector R2 with respect to this axis. So this whole thing, the contributions from these two will be, let's say, tau 1 and tau 2. So this will be so this is how I can see that from this I can understand that the contribution to net torque due to internal forces is 0. Okay. Only external forces. So what we've seen is that if we apply dynamics to each and every particle of this rigid body, okay, and when we wrote the dynamical equation, we just took the cross product with R on both sides. So we converted the F is equal to ma type of equation into a torque is equal to I alpha type of equation, and we integrated over all the particles. Then what we are getting, the result we are getting is that the net torque only depends on the torque because of the external forces. So it is summation R cross F for only the external forces, and that will be equal to the moment of inertia of the body into the angular acceleration. So that gives us the relationship between how angular acceleration is generated because of the application of external forces. Okay, and how exactly the external forces are contributing? They are contributing according to this term R cross F. So they don't depend only on the magnitude of the force. They don't depend only on the direction of the force, but they also depend on where the force is being applied, because it's R cross. So next we will see that we can interpret torque in this way, that torque is moment arm into force. That is the perpendicular distance at which the force is acting multiplied by the magnitude of the force. Okay. So that's the easiest way to interpret the quantity torque. And that's why it is also called moment of force. Okay. By the way, this 0 was for this. I'll explain. It's the perpendicular distance of the force vector from the axis of rotation. I'll explain that. Just extend the line of action of the force and see at how much perpendicular distance it's from the axis. That is the moment arm. So this force is acting along this line. Just extend this line. Now this line is at certain perpendicular distance from this axis of rotation. That is, so imagine this is a three-dimensional body, and I'm applying some force in some general direction like this. So how I'll understand? So from this axis, I'll have to drop a perpendicular on the line on which that force is acting. That is called the line of action. So that perpendicular distance is then called moment arm. We'll write this down. Okay, that's the easiest way to interpret torque. So anyway, this picture is clear, right? Okay. So now moving on, let's look at torque more carefully. Okay. Then we will come to applications of this. Okay. So let's look at the quantity torque. Okay. So we'll start with the definition of torque due to a particular force. Then we'll see net torque. Okay. So how to define torque? This is the symbol that we use for it, where you might be aware that this is the symbol tau, the Greek symbol tau, like alpha, beta, gamma, like that. Okay, so we start by defining torque due to a force F. Okay, like this. Okay. That's how I draw it anyway. And there might be somebody who draws it this way, but and draw maybe this one. I don't know if there are people who are doing that also, but basically it looks like some version of a T. Okay, some people draw it like this also. It's like this. Okay. So torque due to a particular force F about a given axis. Okay. So that is defined as if this is our axis. So you have to understand that our axis is actually like a line coming out of the plane. Okay. And the particular force we're talking about is this one. Then this point becomes what we call the point of application of the force, and R by definition becomes the position of the point of application of the force with respect to the axis of rotation. So R becomes this one. Okay. So the torque because of this force So the word definition of torque is moment of force. But what is the meaning of the term moment of force? It is this mathematical operation R cross F, where R is the position of the point of application of the force F with respect to the axis. Okay, so if I change the axis of rotation, then the same force acting at the same point will create a different torque. Yeah. Yes. Okay. So this is also called No, but that is like moment of inertia is a scalar quantity, no? So it has a different connotation. Okay. Okay, so now let's understand this in further detail, that if we look at the magnitude of R cross F, where theta is the angle between these two. Okay, so suppose now my force is acting like this. Okay, so this is the line along which the force is acting, and my axis of rotation is fixed here. So my R vector is this one. Okay. So this would be the angle in this case, the angle between these two directions. This would be the angle theta I'm talking about. Okay. So one way to interpret this is that magnitude of torque is R sine theta into F. It's a scalar quantity, so it doesn't matter where I place it. Now R sine theta has a very special significance, which you can see in this diagram. If this is the line of action of the force, and I just drop a perpendicular from the axis onto this perpendicular distance here is how much? It is R sine theta, because this angle is theta now. So it is the perpendicular distance of the line along which the force I'm applying with respect to the axis of rotation. So the quantity R sine theta here, it is called the moment arm. It is given the special name. It is called the moment arm of force F. And what it means is that it is the perpendicular distance of the line of application of force with respect to the axis of rotation. So this can be thought of as moment arm into force. Okay. So this one here is our line of application of force. So this is the most intuitive way to imagine what is torque. The more effective the torque is in terms of magnitude, it is according to how much force I'm applying and how far away that force is acting perpendicularly from the axis of rotation. So the greater the moment arm. Okay, so that is why it is more effective to pull the door from here, because the moment arm is large and I'm pulling it like this. From the same handle, if I pull it this way, I need to apply more force, because even though R is the same, but the moment arm is becoming less now. Now my line of action of force is this. So the perpendicular distance from the axis is becoming less. Whereas when I was applying it perfectly like this, that's when it was most effective. Or on the other hand, if I were to put the handle here, then again I'm reducing the moment arm a lot. So the amount of force will not be so effective in applying torque. So the quantity moment arm is this distance over here, this one. It is the perpendicular distance of the line of action of the force with respect to the axis of rotation. Now, alternately, we can also interpret this like this. Now, can interpret it like, so we give the sine theta along with the force instead of with r. And there we'll see the interpretation is slightly different. What we'll do is we'll divide this force into two components, a perpendicular component and a parallel component. Now, the component which is along r, it does not contribute to torque. No, because it's passing through the axis of rotation. So it's r cross, whereas the perpendicular component is contributing how much? That perpendicular component itself into r. No, so that's another way of interpreting. So we'll look at this second interpretation also next. So alternately, what I can do here is, especially in a case like this, it's very helpful where it's like a thin rod or something. Now this is the axis of rotation. Okay. Now suppose I'm applying a force at this end like this. Okay. At an angle theta. And the length of the rod is L. So I want to calculate the torque because of that. So one option would be I'll draw this line of action, drop this perpendicular, so that perpendicular distance will become L sine theta in this case. The other option is the one I'm telling you, that we'll divide the force into two components. This component of force is the perpendicular component, which is F sine theta in this case. Okay. And this is the parallel component, which is F cos theta. Now, as far as torque is concerned, you can see this one plays a role, this one doesn't play a role. Okay, so the torque is simply distance, okay, multiplied by perpendicular component of the force. Okay, so that distance is r into F sine theta. So in this case, that would become whatever the length of that rod is into F into sine theta. Okay. And this is the same thing as this. That torque is momentum into force. It's just about where what is more convenient for us. So if we were to calculate the momentum here, this would be L sine theta. Okay, because the same thing. If we were to calculate this momentum, we'd see that the line of action of this force would be this. So when we drop the momentum, it would be this distance. So it would be L sine theta. So it's just about, yeah. It does not create any torque. Yeah. So that's the derivation we saw now. See, the thing is now we had this on this side. Now we had r cross df, which we integrated now, and this was creating dm into r square alpha. Now imagine if this force is parallel to r cap. So this side is 0. So alpha has to be 0. And physically, what is happening? Physically, this is what is happening. I'm applying the force in such a way that the line of action of the force is passing through the axis. So it does not have any momentum. So it does not create any torque. So this is what this equation is showing you now, that this side is going to be non-zero. Only if this has a component which is perpendicular to r. Sit now, sit. Till now, that's what we've understood. Okay. So this body, if it was at rest, to set it into rotation, it has to develop an angular acceleration like this. So all the particles have to develop tangential acceleration. Got it? Yeah. So that's what we are learning from this dynamical equation. That if this force is only along r cap, it does not contribute to alpha in any way. So there's no way the body will move in that sense. Yes.
It is the distance where the force is applied.
In this case, yeah, I've just imagined this to be a rod of length L. So R is becoming L if the length is L.
What if we applied in
some other point, then I have to take like this. Instead of here, if I was applying at the midpoint, then I would take R as L by 2. So this is just for this particular example. Okay. Now, typically, yes, the question that should arise in our mind is what happens to this F cos theta? It's not contributing to rotation, but why it's not doing anything else? Sorry? It would have a tendency to translate, but is it creating a tendency to translate here? No, no. Why? Because the rod has a fixed hinge here. No? So whenever there's a hinge, there will be some kind of reaction force. No? So basically what happens if I'm pulling very hard on this handle here, it is having some effect on the body. There's a large reaction force that develops here. So if I apply a very huge amount of crushing force, then these two forces together might actually crush the door. So they do have some effect, but it does not contribute to the rotation. So all this parallel component will do is it will create a reaction force at the hinge, which will balance it. No, so this is pulling the rod from that side, so the hinge will pull it back from this side, equal and opposite force. But again, that hinge force will not contribute to rotation because it's acting at the hinge. This R is 0. Okay, so that's another point you can note down here, that in addition here, this parallel component of force will create a reaction force at the hinge. Okay, and that will also not contribute to torque because it's acting at the hinge. So it causes a reaction force R like this. And again, reaction force at a hinge or axis or whatever axle or axis or whatever will not create any torque by definition because its R is 0. So that F cos theta just gets cancelled by the reaction force at the hinge. Nothing happens because of it. Yeah, sure. Okay. Noted. So I'll just read out for you. Okay. So the parallel component of force causes a reaction force capital R at the hinge. Okay. And the reaction force at the hinge or axle or axis, whatever you call it, does not contribute to torque. No, it will balance F cos theta. No? So for example, if that is a force of 100 newtons with this component being 60 newtons or something, the reaction force will also be 60 newtons. So this will create a tension in the rod. No? So the tension at this end will be that much. So the tension at this end will also be that much. It doesn't matter whether it's having mass or massless. No? It's along this direction, along the radial direction, there's no acceleration of the particles. No? So there'll be uniform tension. See, if you were to just pull this rod with 100 newtons of force from this side, would it not create a 100 Newton reaction force here? No. So now in addition to this F cos theta, there's a F sin theta also. So the F cos theta does the same thing it was doing before. It creates a reaction, but the F sin theta now causes the rotation because it's contributing to torque. Okay. Okay, so the two interpretations of torque, right? One is that it is perpendicular component of force into the distance of the point where we are applying it, or the other one is its moment arm multiplied by force. So moment arm is what? Is the perpendicular distance of the line of action of the force. Okay. So let's start looking at our first few applications of this now. So application examples. So this is, let's say, a thin uniform rod, okay, which I have kept hinged to a wall like this, such that it can rotate freely about this hinge. Okay, so at the point P, there is a hinge such that the rod can rotate freely about a horizontal axis at P. Okay. A horizontal axis coming out of the plane of the board. Okay. And the mass of the rod is M, length is L. Now, initially what I have done is I have kept the rod fixed or at rest by application of a vertical external force at this point, which is at a distance of L/6 from this end. Okay. So at a distance of L/6 from this end, I'm applying an external force like this, which is keeping, okay, this rod at rest. It's a vertical external force to keep the rod at rest. Okay. So now, given that mass of the rod is, let's say, 10 kg. And the length of the rod is, say, 1 meter. To find the magnitude of this external force in newtons and reaction force at the hinge, how much that is, what is its direction and its magnitude, take G as 10. So now this is a problem of what we call equilibrium of rigid body, because the rod is at rest and it's not accelerating or it's not angularly accelerating. So when we talk about rigid body being at rest in equilibrium, two things have to be zero. Acceleration of center of mass has to be zero because there's no translation happening. So net force has to be zero. But in addition to that, the angular acceleration also has to be zero. Okay. Now when we have a rigid body with a fixed axis like this one, and that one is in equilibrium, then how we interpret the equilibrium? The only way the body could have moved is angularly, in rotation about the fixed axis. So if it's not moving, if it's in equilibrium, it's not rotating, that means the alpha about the fixed axis is zero. That means the net torque is zero. So how will justify its equilibrium? Because it has a fixed axis. We'll justify the equilibrium of such a rigid body by equating the net torque about the fixed axis to be zero. Okay, so that's how we'll interpret this question. So this is, oh, sorry. This is a rigid body with a fixed axis being at equilibrium. So we will solve for equilibrium by putting the net torque as zero. Okay, so the equilibrium condition for such a rigid body is that the net torque should be zero. Okay, so now we sort of make a new version of free body diagram, and what I mean by new version is that when we have a rigid body in which we are calculating torque, we don't show the body as a particle. We show it with its entire geometry, because where the force is acting and what angle it's acting is important. So we show the forces acting on the rod in a diagram where we're showing the rod as its geometrical shape. We're not reducing it to a particle. And then we calculate the net torque because of all the forces put together about the hinge. So that net torque should be how much? 0. So typically what will happen is some of our forces will be creating clockwise, some of it will be creating anti-clockwise, and the clockwise and anti-clockwise should balance each other. That is the condition for the rod to remain in equilibrium. Right? So can you tell me total of how many forces will be acting on this rod? Which two?
Weight and force.
What about the hinge? There will be some reaction force acting at the hinge, no? It will not contribute to torque, but there will be some reaction force. Na? Imagine this, you are holding the rod by balancing from this side, na? Whereas your mg is acting through the center. So will it not have some kind of interaction with the hinge? Just imagine you nailed it to the wall at that point. Yeah. That's okay. I'm just saying what all forces will be acting at the hinge. I mean, what all forces will be acting on the rod in general. There'll be 3 forces. There is the external force which I'm applying, which I've already told is vertical. Mg will be acting through the center of mass, and that's vertically downwards. Now, let's say I don't know anything about reaction force, but I have to assume that there is some kind of contact at the hinge. So there'll be some third force also that's acting. Now, why is saying that the third force will be vertical? Why it should not have a horizontal component? Because what about the net force on the entire body? That should be 0. Now, 2 of the forces are only in the vertical domain. So how can the third force then have a horizontal component? So that logically tells me that yes, if there is some reaction force, I still have to prove there is some reaction force, but if there is some reaction force, it will act only vertically. Okay. Now see, just think intuitively. I'm supporting the rod by applying a force at one end nearly, L/6, not supporting at the center. So is it not likely that there is some kind of contact between the nail and the rod as they are in? There is some contact. There has to be some contact. No, F will be, that's a different matter. But in general, how many forces will be there? 3 forces will be there. F, mg, and reaction force through the hinge. Now that reaction force, we could have started out by assuming it's some direction like this, but immediately we'll understand that it can't have a horizontal component because net force is 0. Then next thing what we do, equilibrium means net torque is 0. Now when I consider net torque, does the reaction force contribute to any torque? No. So the reaction force is unnecessary as far as torque is concerned. As far as torque is concerned, what is happening? What is F external doing? It's creating an anti-clockwise torque. Whereas what is mg doing? It's creating a clockwise torque. No, it will not be 0. I'll show you that. See how much your F external is coming in terms of weight. So it's less than weight, no? So then how can it balance weight? The center of mass is not accelerating, so net force should be 0, no? So कैसे हो सकता है? Tell me. What is your, see, if your reaction force is 3/5 of the weight and there's no other force, then what is the net force acting on the body? 2/5 of the weight, no? So shouldn't it have a downward acceleration? But it's not having, no? Why? Because there is some reaction force. Okay. Another way to understand, see, I'm applying the force like this, no? Isn't it giving the body a tendency to tilt like this? So this point in the body, will it not push against the hinge downwards? So the hinge will have to react back. Okay. So my free body diagram, now, I mean, the term free body diagram changes a little bit now because we are not going to show only the forces acting as if the body is a particle at the center of mass. We're going to show it like a full rigid body, okay, with the forces acting at whichever particular points. So center of mass ke through mg will be acting. Okay. Now, if you were to consider only these 2 forces, you'd realize that there's some kind of imbalance. The object is balanced, so there has to be some force on this side also, and that is the reaction force which is acting through the hinge. Yes.
But the reaction is not contributing to torque. So even though the net along
Reaction does not contribute to torque, but it contributes to net force, no?
Just a moment. What does net along y have to do with torque?
No, it doesn't have to do with torque. It has to do with the acceleration of center of mass.
So why isn't the reaction just contributing to torque?
Why doesn't the reaction? Because its momentum is 0, no? reaction force is acting at the hinge, no? So it does not contribute to torque. Okay. But the body is also at rest in terms of translation. No? On not only its alpha is 0, but its acceleration is also 0. No? So net force acting on the body should also be 0. So that's where the contribution of the reaction force is coming in. You understand it? So now what we'll see here is that, okay, first thing, alpha is 0. There's no rotation happening. So net torque, okay, about the hinge P, this should be 0. Okay, now about the hinge P, it's very easy. What is this force's line of action? It is 5/6L. Okay, so F is creating, okay, what type of torque? Anti-clockwise torque. No. And mg, its moment arm is how much? L/2. Okay. So clockwise and anti-clockwise torque are balancing each other. Okay, so this tells me how much force I need to apply. The magnitude of the force I need to apply is 3/5 of the weight.
Reaction force, what would happen?
Alice. Okay. If there's no reaction force, that means there is nothing, there is no hinge over here. Okay, now without a hinge, try to balance a body like this. You won't be able to balance. See? Whatever force you apply here, it will, yes, it will go into translation plus rotation. It's not like that. Without, the question is not without reaction force, what would happen? The question is that there is a hinge here. No? So how does the hinge react to the application of this force? It reacts by applying some kind of reaction force. And how we know that that reaction force is vertical? Okay, so this torque equation does not give us any information about the reaction force. Which one gives us the information now? The second thing, that the acceleration of the center of mass is 0. So net force on the center of mass should be 0. So that's why this cannot have any horizontal component, because these two are vertical by definition. But you can see these two are not balancing each other. No? This is only 3/5 of the weight. So what is balancing mg minus 3/5 mg? Is this. So again, reaction force is a self-adjusting force. No? It's like normal reaction. It adjusts itself according to the condition. So because I'm applying 3/5 mg over here, the reaction force is so much. Now next I will show you, the moment I remove this force, this body will start rotating. And the moment it starts rotating, the value of the reaction force will change. It will not remain 2/5 mg. Yes.
So you said that F external and mg will balance each other
In torque.
but it will not balance each other for the reaction.
No, not it. They will no. See, they will not balance each other as far as translation is concerned, because this one is 3/5 mg. No.
So that was we considered the torque part for the pure rotation.
Yes. So this equation has come from which condition? That we are observing the body is not accelerating. I mean, it's not having any rotation. So why it's not having any rotation about the axle? Because we have applied that much force required to make the torque 0. Instead of applying a force of 3/5 mg, suppose I applied a force of mg over here, then what would happen? It would start rotating. It would have alpha like this. If I applied a force of, let's say, 1/2 mg, then it would start rotating like this. I have to apply exactly this much force if I'm applying it at this point. If I'm applying it at some other point, I have to again adjust the value of force, no? So that it just creates the required amount of anti-clockwise torque to balance the clockwise torque that mg is creating, which is how much? Mg L/2. What my point now? No? Okay, now what is also happening is that, okay, I've applied this force, I'm keeping this at rest, but the combination of these two forces is having some effect. No? There is a net downward force pulling the rod down. That is how much? Mg minus this force. So where that force is going, it's resting against this surface, no? Of the hinge.
Why is there a net torque?
Because mg is greater than F external. No? So this is 3/5 mg. No?
Okay.
Okay, so there is some net of these two that is pushing this down still. No? But why you don't see it moving down? Because this reaction force is balancing it. So the next thing that we'll see is, apart from the fact that alpha is 0, we are also seeing that what about the acceleration of the center of mass? It's 0. So net force should be how much? Is 0. Okay. I mean, just because we are applying rotational dynamics to a body which is having a fixed hinge, it doesn't mean that what we have learned in dynamics earlier does not apply. No? What applies what we've learned in dynamics applies. It's a rigid body which is at rest. So apply dynamics, net force is equal to rate of change of momentum. Rate of change of momentum is how much? 0. So the net force on the body should be how much? 0.
So
Now this reaction force does not contribute to torque, but it contributes to net force. No? So now the second thing here is that the acceleration of the center of mass is 0. Okay, yes, tell me.
So the net force along the y-axis will influence both translation of
अरे net force जिस भी direction में होगा, the center of mass's acceleration will be in that direction. Now suppose I drag this in a direction like this, then the center of mass would have a vertical component of acceleration. It's not this, no, it's what the net force is that determines the acceleration of the center of mass. So here, since the acceleration of the center of mass has to be 0, the reaction force has to adjust in such a way that makes the net force 0. Now what is this net force? It is the vector sum of reaction force, the external force that I am applying, and the force that Earth is applying on the body. This has to be 0. It's not for us. It is the way it happens. The reaction force is a self-adjusting force. So it always adjusts according to the required condition. So here it adjusts according to that condition required. That to balance the torque, I have to apply this much force over here, which is only 3/5 of the weight. So to keep the rod balanced, how much reaction force is required from that end? It automatically it adjusts itself to create that balance force. Understood? So now,
in the second case, we are taking it like a particle,
like a body, which is like system of particles.
like the
Yeah, you can do that. You can make an FBD that way also. But basically, see, in system of particles, we saw, what is the dynamical equation for a system of particles? That the net external force is rate of change of its momentum. So on this rigid body, which is a system of particles, the net external force is the sum of these three, and its rate of change of momentum is 0. Okay, so reaction force plus this minus mg should be 0. No? So what is this now telling us? That the reaction force is vertical and its magnitude is how much? 2/5 of the. Okay, understood this now? So the torque balancing part is very simple. That is easy to understand because there's no rotation happening about the fixed hinge. So net torque has to be 0 and reaction force does not contribute to torque. But how do we understand how much reaction force is acting? That comes from looking at the translational part of the motion. This is the rotational part. There's no rotation, but also translationally, there's no motion happening. No? So no translation means acceleration of the center of mass is 0, which means that the net external force on the rigid body should be how much? 0. So if there was no reaction force, you see that condition is getting violated. No? So logically, you understand that there's only one possibility left, that the reaction force has to have a vertical direction and it has to have a magnitude of 2/5 mg. Otherwise, we cannot observe that the center of mass is at rest. Otherwise, it would have some kind of acceleration. Understand? Now, how it develops, that is the magic of reaction force. Right? It always self-adjusts. What my point?
So we just need a force to keep it in equilibrium without influencing the
Yeah, and it will always adjust itself. No? Like suppose I do something else now. Suppose I hang a weight from somewhere here. Then to keep it in equilibrium, I'll have to increase this force. Okay. Again, the reaction force will self-adjust. And it will adjust according to both the things, the amount of weight I've hanged and how I've adjusted this external force. Unless, of course, it cannot adjust, like the hinge might break or something because it can't provide that much force. That's a different matter. Okay, now let's come to the second part of this question. Now, while this is in equilibrium initially like this, now suddenly we withdraw this external force. So what we'll observe? We'll observe that the rod goes into this kind of motion. So immediately when we release that force, now it sets off with some acceleration. So it's in that kind of motion that its initial velocity is 0, but in this case, what velocity? Angular velocity, because it's an angular motion. So it will go into pure rotation about this, but in such a way that the initial angular velocity is 0, but there's some angular acceleration. And that angular acceleration is created by what? It's created by mg. So we will find out that angular acceleration. From that, we will find out the acceleration of the center of mass. And from that, we will calculate how the reaction force changes at the instant when we just release the external force. Okay. So let's come to that part of this question. So now this rod is suddenly released from this position. All of a sudden, we release it from this horizontal position. So F external is suddenly withdrawn. So find angular acceleration of the rod, the acceleration of the center of mass, and the reaction force R at the instant when the rod is just released. The rest of the things are the same. Its mass is m, length is l.
So your topic keeps changing.
Yeah, in general, it will keep changing from point to point. So it will have a variable angular acceleration. As it's going down, you can visualize that the momentum of mg will keep reducing. By the time the rod becomes vertical, that momentum becomes zero. But we have to calculate only at that instant when we just release. Okay, following. Little sleepy. What happened? Acha. So you must have had a morning lecture also, no?
So we done today.
Acha. So now which equation we use for alpha? Torque is equal to I alpha. Okay. And about the hinge, how many forces are creating torque now? Only one force, na mg. The external force have withdrawn. So torque because of mg is equal to moment of inertia into alpha. The moment of inertia about one end of a rod, remember we have calculated. How much it is? ml square by 3.
12.
Na? Good. 12 is center of mass.
Oh, sorry, sir.
One end is ml square by 3.
3.
It is that dm x square integrated from where to where? X equal to 0 to L, no? Not minus L by 2 to plus L by 2. So use that value, ml square by 3 is the moment of inertia about that axis. So torque is how much? mg L by 2. Right? Torque because of gravity is gravitational force into momentum. So at that moment it's not yet rotated, no? So it's still at L by 2. So mg L by 2 is your left hand side torque, and right hand side I alpha. I is ml square by 3. So alpha, how much you're getting? 3g by 2L, right?
Yes, sir.
So length, I think I had given 1 meter, and g you can take as 10. So you can get the alpha in radians per second square.
So what could have provided tangential acceleration here?
Very good question. We'll come to that. mg is acting, no? mg is acting tangentially. That is only providing tangential acceleration. But you see the tangential acceleration is going to be less than g, which means that the net force acting is less than mg. That means there's still some reaction force.
On the okay.
Okay.
It's a little hard to imagine. There was no-
It's a little bit new. That's the only thing. Okay. You'll get used to this and okay, so first of all, we are just setting off the motion right now. So the angular speed is 0. Okay. But because we've withdrawn the external force, so the weight acting through the center of mass, it is creating some torque. So it's creating some alpha. Okay. So if this point where it is hinged, we are labeling it as P, torque about P is moment of inertia about P into alpha. That P is that hinge point. Okay. So torque will be what? Torque will be torque because of weight alone. So mg into L by 2 is the clockwise torque it's creating, and moment of inertia about one end of the rod. Okay. So the alpha that I'm getting is clockwise. Okay, so I'll get a clockwise alpha of 3g by 2l. Okay, so that's how much? 30 by 2, no? 15 radians per second. So working it out numerically, because L was, yes. So getting these values. Okay, now the interesting thing is there will also be still some reaction force at the hinge, because you can see that the center of mass will have a tangential acceleration. That will only be the acceleration of the center of mass, because centripetal acceleration will be 0. Why? Because omega is 0. So the center of mass has a point at that instant. It's starting its circular motion at a radius of L by 2. So how much will be that tangential acceleration? It will be L by 2 alpha. Okay, so from that we can see now that the center of mass is acceleration. So that is that's going to be 3g by 4 vertically downwards. So just at that instant, the center of mass will have an acceleration vector which is pointing down, and that's equal to 3g by 4. Right. So from that we can now calculate how much the reaction force will be, because net force is equal to mass into acceleration of center of mass. So net force is how much? mg minus r. Yes, no, because we just withdrawn the force. No? So it started from rest. So its initial angular speed is 0. So that's why there's no centripetal acceleration as yet. Okay, but it's set off with the tangential acceleration. So the center of mass as a particle, it's in started its circular motion at a radius of L by 2. So it has a tangential acceleration of L by 2 alpha, and that's vertically downward. So now when we apply dynamics, we'll see net force is equal to mass into acceleration of center of mass. So net force should be that much downwards. No, so that's how I know that the reaction force is upwards, because this acceleration is less than g and is pointing down. Okay, so this is written down. Okay, so let's talk about the reaction force now. Again, same thing. No? You're seeing that as a result of this motion, the center of mass, what is its acceleration? Is it g? No, no. So then it can't be in free fall. If it's not in free fall, there must be some other force. No? That's the thing. No? If there was no reaction force, then two things would happen. First of all, there would be no rotation like this happening. So there's no contact at the hinge. And secondly, the center of mass would be in free fall. Its acceleration would be G. Okay. So yes, so the acceleration of the center of mass now is 3G/4. No? So when we apply this equation, that the net external force is equal to, okay, so what do we get from dynamics here? We get that mg minus r is equal to m into pg/. Okay. So we get that the reaction force has reduced to 1/4 of the weight. Okay, which is quite a bit less than what it was when we were applying that other force. No? It was 2/5 of the weight. So it was 0.4 you know, times mg, and now it's become 0.25 times mg. So suddenly in a flash, the reaction force has changed. No? The moment I withdrew the external force, the reaction force has changed, and the whole thing is set up into motion. The center of mass is no longer at rest. It's immediately right now the vector ACM is what? It's a vector downwards of 3G/4. Yes.
Can I say this reaction force is the maximum that we use to apply?
For this motion, yes, because as the rod starts rotating, now the reaction force will become lesser and lesser. ACM will become lesser and lesser. Okay. But
So reaction force is less.
no, not necessarily. Okay. One will have to check that out actually. There might be a maximum minima situation also. Anyway, so now we will do another type of application and you will understand this thing yourself. Okay. Now, after some time, let's say the rod has rotated through some convenient angle, let's say 53 degrees or something. So by the time the rod has rotated through an angle of 53 degrees, so its angular displacement is 53 degrees, starting from here only. So now what is the angular speed of the rod? Okay. What is the velocity of the center of mass? Okay. What is the alpha of the rod? And what is the acceleration of the center of mass? Okay. So find omega and VCM. Okay. At the instant when angular displacement and we'll also find alpha and acceleration of center of mass at the same instant. Okay. Now you yourself said that the alpha is a variable quantity, no? Because the momentum is changing. So is it going to be useful to use kinematics? No, because there is variable alpha. So what other option we have? We have work energy. So think if you can use work energy here. It's a free hinge, no? It's rotating freely about the hinge. So there's no non-conservative force like friction or anything. That means mechanical energy can be conserved. As the rod is rotating, center of mass is coming down, no? So gravitational potential energy is reducing, and that's converting into kinetic energy. Yes.
So the reaction force is mg/4, right? So the rod is actually falling also.
But reaction force is not doing work, na beta?
No, sir, not in this case.
Ah. So that is the instantaneous acceleration of the center of mass. No? It's downwards 3G/4.
So the net force along the y axis is not zero, right?
तभी तो non zero है ना, because the center of mass has a vertically downward acceleration.
In this case, you know,
This case it will change. I never said reaction force will remain.
falling while rotating.
It's changing, na? The vector is changing from point to point. So accordingly, the forces are changing.
That's what I'm saying.
Just forget about reaction force for a moment. Okay, I'll show you reaction force in this diagram, that you will understand. Okay.
The rod will not fall.
The reaction force is mg/4 only at that instant. After that, it changes value. In fact, after that, it will start having a horizontal component also. Because the center of mass's acceleration will have a horizontal component. Just do an experiment like this. Now, see, as this rod is rotating, how it applies force on your fingers over here. You see, it applies a pulling kind of force. So its direction is initially only vertical, but it starts changing toward this kind of direction.
Immediately after we remove the force, the net y should be zero, right? It will fall.
Again, you're confusing center of mass with the hinge. The hinge is at rest. The center of mass is not at rest. And the center of mass has a vertical acceleration. The CM is not at rest, no, Baba. Center of mass is having a downward acceleration. Where it's losing energy. Kinetic energy is increasing, na? And potential energy is decreasing. Only difference is what type of kinetic energy it is now. Rotational kinetic energy. So what is the formula of kinetic energy? Half I omega. Reaction force is doing work, is it? What about the point of application of reaction force? Now remember, in work energy, I had warned you once that work energy I've got no. Okay, so in work energy now, when we see that definition F dot ds integration for work done, what is the ds of what? No, not necessarily. It is the displacement of the point of application of the force. Okay, so the point of application of that reaction force is not moving, so it does not do work. The point of application of mg is moving, so it's doing work. Okay, it's like this, na? In work done, na, when we consider integration f dot ds, so you can just make an additional note of this point here. This ds is the differential displacement of the point of application of the force. Okay. It's not the displacement of the center of mass of the body on which the force is acting. Okay. In particle dynamics, it will not make a difference. So it's a particle is a single point. So wherever the force is acting, that's the same point as the particle itself. But in rigid body dynamics, it makes a difference. Or for example, even in non-rigid body dynamics, if you have a piece of sponge and you're pushing it with force from both the sides, so the center of mass is maybe not moving, but the forces are doing positive work, and that work is getting stored in it as elastic potential energy. So why is they are doing positive work? Because of that reason, because the point of application of the force is moving. Okay, so this is very important over here, that when we use the general definition of work done by a force, in that the ds vector is the displacement of the point of application of the force. So you see here the reaction force's point of application is not having any displacement, it's remaining the same. In fact, reaction force will change in magnitude and direction, but it will not be doing any work. Okay, so now let's come to the application of work energy. So the center of mass is moving from here to now here. So how much is the displacement of the center of mass vertically? It is this this will be theta, no? So it will be L by 2 sine 53, correct? Let's just check it out. So the rod was originally here, okay, and its omega was 0. Okay. Now rotating about the hinge, it has come to this position. Okay. So by now it has an angular speed omega. So the center of mass has moved from this position to an angular displacement theta. Okay. Like this. So vertical displacement of the center of mass is how much? L by 2 sine theta. Okay. So this H is L by 2 sine theta. Okay. So because kinetic energy of rotation plus gravitational potential energy is conserved. The conservation of energy being applied here. So change in kinetic energy plus change in gravitational potential energy is 0. So going from here to here, plus half I omega square minus mgh is equal to 0. Okay, so half into ml square by 3 omega square will become mgl into sine 53, which is 4 by 5. We are taking theta as 53. So let's see what we are getting. So parametrically, omega is becoming how much now? 24 by 5 g by l square root, right? Just check my working. Is this correct?
So that's L by 2.
Sorry, L by 5. Sorry. So this will become L by 10. Yeah. Yeah. Okay. Now is correct? Okay. So this is 12 by 5. So this is my angular speed. Okay. Or this is omega. So now what about VCM? Tangential velocity, center of mass will have. It's in circular motion. Parametrically it will be like this. Okay, so this is done. Okay. Now come to the next part where you want to calculate alpha and ACM. Okay. You want to convert this to vector notation, you know how to do with unit vectors. Huh? Like if you take x and y like this, then our velocity of the center of mass will be like this, where I think this angle will be theta, isn't it? Okay, so you can always convert it to vector using that. Minus sine 53 I cap minus cos 53 j cap हो जाएगा उसका unit vector. Right? So if you want to convert this to a vector form, you can do that also. Now this will require something different now. No? To calculate alpha, what we'll have to use? Here we use work energy to calculate omega because alpha was variable. But to calculate the instantaneous value of alpha, what we'll need? We'll need the torque equation. So we'll again have to calculate torque is equal to I alpha, but at the new instant when theta is 53 with the horizontal. So moment arm कितना हो जाएगा mg का? It will become mg L by 2 the moment arm will become L by 2 cos theta.
Ah,
You know? So mg L by 2 cos 53 should be equal to I alpha. So that will give you the value of alpha. And once you got alpha, now think how you will get the acceleration of the center of mass. Because now the body is in motion. So the center of mass is in circular motion with some omega and alpha. So it will have both the types of accelerations, tangential and centripetal. So separately you will calculate centripetal component of acceleration from omega that you got here. And separately you will calculate tangential component of acceleration from the alpha you will get in the second part. And from that you will calculate the net acceleration of the center of mass. Right? Okay, so now so line of action of mg is this one. And this angle was theta. So the moment arm for mg will be this. So it will be L by 2 cos theta. That will be the moment arm, right? So mg is creating a torque. Come in. Okay, so this torque will be so alpha is becoming 9g by 10L, is it? This is the angular acceleration I'm getting at theta equal to 53 degrees. Okay. So now once that is happening, coming back to the acceleration of the center of mass, I'll see that the center of mass has two components of acceleration. It has tangential acceleration and centripetal acceleration, because it has an omega also. And therefore the net acceleration of the center of mass will be the vector sum of these two, which might be in any sort of direction like this. So the center of mass is acceleration. Okay. It's crazy. Okay, so acceleration of the center of mass will be the vector sum of tangential plus centripetal acceleration. Okay, so the magnitude will be square root of tangential square plus centripetal square. Okay, and now you can see here that the centripetal will be omega square L by 2. Okay, so remember omega square L was how much? Omega square was how much? It was omega square was this thing 12 by 5 na G by L. So this will become 6 by 5. This will be the centripetal component of acceleration. Okay, and tangential acceleration will be L by 2 alpha, and alpha we just saw is that, so it is going to become 9 by 20 G, right? In terms of G, I'm saying. So you can see it has a pretty large magnitude of acceleration. Like this component of acceleration itself is greater than G, and this is little less than half of G. I'm not going to get into reaction force here because it's complicated, but you can understand that the net force has to be in this sort of direction, on the whole body, and mg is acting only like this. So the reaction force will have to have a horizontal component and a vertical component, and it will not necessarily be aligned with the rod. So that is the difference between having a particle attached to a thread. So the tension is always along the thread, and having a rigid body with a hinge. The direction of the reaction force is not always along the rod. Okay. So we'll come to those kind of questions a little bit later, they're a little bit more advanced. Okay. So in the meantime, let's look at one more question today. That's how this works now. So this is a smooth wall and a smooth floor. Okay. And we are keeping a rod like this. Now you'll realize that it has a tendency to slip like this because of gravity. I have a tendency to slip. So let's say we are preventing it from slipping by applying some kind of an external force horizontally like this. Okay, so we are keeping this rod of mass m and length L. Okay, so the rod is kept stationary against a wall. At let's say theta equal to, let's take an easy example, 45 degrees. Okay, mass of the rod is 10 kg. Find the external force with which we are pushing this end. Just, let's say the rod is against the wall and you're keeping your foot or something against it. So your foot is pushing horizontally against it. So how much force is this? So again, it's equilibrium of rigid body. Okay, but this time the interesting thing is it does not have a fixed hinge. It's not a hinged body, no? So torque is 0. Now we are free to select any axis we like, because we are not seeing alpha about any axis now. So we can select any axis of choice. So net force should also be 0 and net torque should also be 0, because neither there's rotation nor there's translation. But at the same time, when we are balancing net torque as 0, we can take any axis which is convenient to us. We can take the center of mass axis as a default axis. Yes. Write the question, then you'll understand why we need to take torque. Okay, because just translationary equilibrium alone will not give you enough equations to understand what all forces are acting and how much force is needed. Okay. So this is an example of, again, equilibrium but this time of a free rigid body. Okay. The condition for this is that net force will be 0. Okay. And net torque is 0. And this net torque can be taken about any convenient axis. You can see we know only one information, the weight of the rod and the angle theta. There are too many unknowns over here. There are 2 normal contact forces and there's the external force F. So 3 unknowns. So our equilibrium, I mean translational equilibrium is not going to generate enough equations. No? We'll take 2 components. So 2 equations will come from there. The third equation is required from torque. Now, if nothing else strikes you, you can always take the center of mass as the default axis to balance torque. No. It's in contact with the surface. The surface will apply a normal force, no? Perpendicular to itself. Just imagine the rod against the wall. Is the rod not pushing the wall like this? Wall is pushing it back. It's in contact, no? Same with the floor. So there is one normal force like this acting on the rod, that is, okay. There's one normal force acting like this. Okay. And there is its own weight acting through the center. Okay. Let's say this end of the rod is A, this end of the rod is B, and the center is C. So when I write the net force as 0, because acceleration of the center of mass is 0. Now horizontal equilibrium will come from the fact that N1 balances F. Vertical equilibrium will come from the fact that N2 balances mg. So out of my 3 variables N1, N2 and F, I have only 1 from these 2 equations. Okay. Now the fact that net torque is 0. Okay, this. You can take torque about any axis. Now here, which axis will be most convenient? If I take an axis through B, because 2 of my forces are acting through B, then these 2 will not contribute. So about this end, what is happening? Mg is creating anti-clockwise and N1 is creating clockwise, and they should balance. Okay, so I can take net torque about B. Suppose I take that as 0. I can take about C also, and you can solve it later and you'll see you'll get the same solution. Okay, but the equation will come in a different form. So about the point B, you can see that when we do the torque balancing about the point B, you have to consider mg. Okay. So the moment arm for mg will be this L by 2 cos theta, because this angle is theta. Okay, and the other force which is creating torque is this N1. Okay, जिसके लिए moment arm ये हो जाएगा. In this case, theta is very convenient, so sin theta and cos theta are the same, so it will not matter. But okay, so N1 is creating a clockwise torque. Okay, and mg is creating an anti-clockwise torque. And these 2 forces don't create torque about the point. So when I write this torque balancing equation, I have mg into L by 2 cos theta, which is creating the anti-clockwise torque, is balanced by N1 into L sin theta, which is creating the clockwise torque. So in general, I have the equation that N1 is equal to mg by 2 cot theta. I've taken an easy case where theta is 45 degrees, so cot theta is 1. So I'll get exactly mg by 2. So now this is my third equation. And you can see 3 equations, 3 variables. So finally, I'll get the solution that N2 is equal to the weight, which is equal to 100 newtons, and N1, which is equal to F, is equal to half the weight because theta is 45, and so they are equal to 15 newtons. But if I wanted to keep it at, let's say, 37, then again the forces would be different. N2 would be the same because it's equal to mg, but that N1 and F would have changed. Okay, now you will also get the same result by, but the problem is if you balance talk about the center of mass, yeah, that will also work. You see that about the center of mass, now N1 and F are creating anti-clockwise torque and N2 is creating clockwise torque. Now you can balance talk about this point also, then these 3 forces are creating torque. You can do something very unnecessarily complicated for yourself by taking some point in between here and balancing torque. So all 4 forces are creating torque, but you'll see all of them will give you a consistent set of equations. What you cannot do is take torque about 2 points and use one of those 2 equations, because torque about 2 points will give you 2 equations which are consistent. So you won't get a simultaneous solution of them. You'll have to write one equation for horizontal balancing, one for vertical balancing, and one for torque balancing. Torque you can take about any point. Another very convenient point for torque you can take is this point, though it's lying outside. You can see F is not creating any torque about this point, and the other 3 forces. But the most convenient point here is B. Okay, so if you have a free rigid body, remember when it's in equilibrium, the net torque is 0, and you can take access of any axis of convenience. So if you see a diagram like this, which is the one which is most convenient, a point through which multiple forces are acting. Okay, then your torque equation will have minimum terms, right? Yes.
So if it is to follow the surface as the axis, how would the rod move?
No, so suppose this was slipping, it would be moving like this. So it would be in a combination of translation and rotation. Now, if you look at the orientation of the rod with respect to an axis through this point O, the angle is changing. So it is in angular motion. So interestingly, actually, even if a body is in free fall, about an axis outside it, it is in rotation. So this angular position is changing. See. So if I take an arbitrary point here and this object is just falling freely along its length, even then I'll say that about this point it is in rotation. It's in a combination of rotation and translation. Because the angular position is changing. Now, what is the meaning of rotation? That theta should be changing. So theta is changing. But if I see a point here and it's moving along this line, then about that point there is no rotation. So it is all about which axis you consider also. Okay. So that's why we will later see that translation or linear momentum of a particle also results in angular momentum about some axis. And that comes by taking moment of linear momentum. So R cross P, like you've taken R cross F for torque, like that R cross P for linear momentum gives us angular momentum.
So can you say that every object is over the
Yes, you can say that. Like even a straight line motion is ultimately a circular motion with radius tending to infinity. So in that sense, everything is interconvertible, right? Okay. Okay. So hope this is clear, people. Okay. So that's it for today's session. We'll pick it up next week from here. And also in the meantime, please complete questions from system.